Hello again. So we're not going to work extensively with limits. The way things work is that we use them to define a few things, to define the derivative, to define the integral, and then we work with the derivative and we work with the integral, and limits kind of fade into the background. But we should know in a general sense how to work with limits. So here are some what we might call limit rules. Um, it's easy to take the limit of a constant. The limit as x approaches c of a constant is just the constant. Like the limit as x approaches 3 of 5 equals 5. Because what happens as x gets closer and closer to 3? Well, as x gets closer and closer to 3, 5 stays 5. X changing and x getting closer to 3 has absolutely no effect on this number. The limit as x approaches c of x equals c. For example, the limit as x approaches 2 of x equals 2. Because as x gets closer and closer to 2, as x is getting closer and closer to 2, what's this function x doing? Well, it's kind of silly even to say as x gets closer and closer to 2, the function x gets closer and closer to 2. So, and then let me try to go in the same order as my notes. Suppose we're taking a limit and we've got a function and we've got a constant in front of the function. Then this limit is the constant times the limit of the function. So for example, the limit as x approaches 3 of 5x. So we've got a constant 5 and we've got a function x. What this rule is saying, a little more informally, is that we can pull constants in front of limits. This is 5 times the limit as x approaches 3 of x And the limit as x approaches 3 of x, this is an application of this rule. The limit as x approaches 3 of x is 3. So this limit is 5 times 3, or 15. This is really a special case of another rule. Algebra works well with limits. I mean, not algebra, arithmetic. Addition, subtraction, multiplication, and division. Division has an asterisk next to it. But the limit as x approaches c of one function plus another function is the limit as x approaches c of the first function plus the limit as x approaches c of the second function. And at the moment, we're pretty limited in the applications we can do. Let's let x approach 7. And let's look at the limit as x approaches 7 of x plus 3. So this is addition, and the limit of addition is addition of the limits. And then these are both limits we can take. These are applications of the first two rules. The limit as x approaches 7 of x equals 7. The limit as x approaches 7 of 3 is 3. And this limit is 10. And we have similar rules for subtraction and multiplication. The limit of f minus g is the limit of f minus the limit of g. And the limit of f times g is the limit of f times the limit of g. And you'll find examples in the textbook. The fourth arithmetical operation is division. And here's where there's an asterisk. The limit as x approaches c of f of x divided by g of x. Well, it's what you might expect based on these other three rules. It's the limit of f divided by the limit of g. But here's the asterisk. If the limit as x approaches c of g of x is not equal to 0. So let me see if I can, give me just a second. Here's how we introduced limits. And when we introduced limits, we had division. The example we did was the limit as x approaches 3 of a height function at 3 minus, we used b instead of x, but minus a height function at x divided by 3 minus x. Well, this is division, but we cannot use this rule, because if we try to use this rule, we get a division by 0 error. The limit as x approaches 3 of the denominator, we can break it apart just as we broke apart this limit up here. The limit as x approached 7 of x plus 3. This is the limit as x approaches 3 of 3 minus the limit as x approaches 3 of x. This limit is 3. This limit of x is also 3. So we cannot use this rule. And it's sort of a frustrating irony, not really irony, but I don't know a better word, a frustrating fact of mathematics that we learn all of these limit-taking rules and then they don't work with the limits we care about. In particular, the limits we care about the most in differential calculus are the limits of quotients, and we're never going to be able to use this rule because they always get hit with this exception. The limits of the denominators in the examples we care about are always going to be 0. So it's, well, what can you do? It is what it is. Any more limit rules? Just one for now. The limit as x approaches c of a function raised to a power is the limit raised to the power. And incidentally, this is true because powers include roots, like the square root is the 1/2 power, the cubed root is the 1/3 power, and so on. This is true for roots and integer powers. The limit as x approaches 2 of 4x plus 1 to the 3rd power. According to this rule, this is the limit raised to the 3rd power. Now we've got the limit of a sum. So this is the limit of 4x plus the limit of 1. Now we've got the limit of a constant times a function. So this is 4 times the limit plus, I'll just write this, the limit of 1. This is all still being cubed. And now we can take these limits. This is 4 times 2 plus 1 cubed. So that's what? 9 cubed, whatever that might be. 729. Now, one last thing. Now, I won't keep my videos super short. As part of this problem, we took the limit as x approaches 2 of 4x plus 1. And what we ended up finding was that it was 4 times 2 plus 1. Now, ordinarily, to find the limit as x approaches c of a function, we do not compute f at c, right? That's part of, I can't find where I wrote the definition of a limit down, but when I wrote down the definition of a limit, I said we're letting x get closer and closer to c, but not equal c. And we saw why that was so important when we looked at the velocity example. We can let x get closer and closer to 3, but if we let x equal 3, we get a division by 0 error. Notice, though, even though I'm saying this, if f of x equals 4x plus 1, the limit as x approaches 2 of f of x is 4 times 2 plus 1, which does equal f of 2. So this statement that to find the limit as x approaches c, we cannot just stick c in there. This is a statement that is true in general, but it has exceptions. So let me state one final result. If p of x is a polynomial, the limit as x approaches c of p of x is just p of c. We can just stick the limit in, the number in, as long as this function is a polynomial. As long as this function has the specific form a sub n x to the n plus a sub n minus 1 x to the n minus 1 and so forth. And I said one last result, and that was a lie because we have a similar result for rational functions. But the result for rational functions, first of all, what is a rational function? A rational function is a polynomial divided by a polynomial. And when we were talking about limits of quotients, we said, well, we've got this asterisk. We can't divide by 0. So the second result also has an asterisk. If R of X is rational and R of C is defined, then the limit as X approaches C of R of X is just R of C. And in a later section, we'll see that polynomials and rational functions aren't unique. We'll see there are other types of functions whose limits can be computed in this nice, quick way, and we'll give those functions a special name. But for now, adieu.